Hello students, in this video we are going to study about the magnetic field due to a toroidal solenoid, or we can say it a toroid. Before this we have studied about solenoid. So solenoid was a structure made by winding insulated copper wire closely in the form of a helix. We called such structure a solenoid, and sometimes we call it as a long solenoid when its length is much greater than its diameter. So that was the solenoid. Now here we are studying about toroidal solenoid. So what is toroidal solenoid? Whenever we have a solenoid and we bend it in the form of a closed ring, then it becomes a toroidal solenoid. So basically we are going to bend a solenoid, or we are going to hold its ends and join together in the form of a ring, or to form a closed ring kind of structure. Then that type of structure is called toroidal solenoid or toroid. I am going to show it here in the diagram. So here in the diagram we know that this is a solenoid, and if we hold its end and bend it together, then it form a ring like structure like this. Then we called it as a toroidal solenoid, or simply a toroid. So we can define a toroidal solenoid as a solenoid bent into the form of a closed ring. Then such kind of solenoid is called a toroid or a toroidal solenoid. If we take the ends of this solenoid and bend it together to form a closed ring, then this kind of shape is called a toroidal solenoid or a toroid. Let me show you the sectional view of this solenoid. So this is the sectional view of a toroid, in which these dots represent that the current is coming out of the plane of the paper, while these crosses represents that current is going inside the plane of the paper. Or we can say that the toroid is formed by winding the wire over it such that the current is going like this. Okay, so it is coming out from the plane of paper from these points and entering the plane of paper at these points. So it's like this, it's moving like this. This is the sectional view of the toroid. Now our task is to find the magnetic field because of this toroid. So the region, the whole region because of this toroid is divided into three kinds of spaces. Like the first space is the open space interior to the toroid, or this open space that is interior to the toroid. The second space is actually inside the toroid, so we call it the first space, and this is the second space. Second space is the inside the toroid, while the third space is the open space exterior to this toroid, means this whole this space that is exterior to this toroid is the third space. So we actually have to find three magnetic fields separately, magnitude of magnetic field in the three regions separately for region 1, 2 and 3, one by one. Okay, so our task is divided into three sections, case 1, 2 and 3. One is for those points that are in the open space interior to the toroid. Second is for those points inside the toroid, and third is for those points in the open space exterior to the toroid. All right, so let's start doing this one by one. So I am going to show you the magnetic field, how is the direction of magnetic field inside the toroid. And if we have to want to apply ampere circuital law to find these magnetic fields, we have to form Amperian loops for each of the case. Okay, so here in this diagram, the blue dashed line circles are the Amperian loops that we form to find the magnetic field in these regions. So for region 1, the Amperian loop is this of radius r1, we call it as loop 1. For region 2, the Amperian loop is this of radius r2 and we call it as Amperian loop 2, and for region 3 the Amperian loop is this of radius r3 and we call it as loop 3. We also consider some random points in these regions, that is P, S and Q, to find the magnetic fields. So start with region number 1. Let's so for first case we are going to find the magnetic field, the magnitude of the magnetic field for points in the open space interior to the toroid, means this region. So we are going to find the magnetic field at any point P. For this region, let the magnetic field's magnitude is B1. Okay, so what we are considering for region number 1 or for this space, we are considering that the magnitude of magnetic field is B1 and this Amperian loop is present here of radius R1. Okay, now the length of this loop, is actually the circumference of this loop. So we consider the length of this loop is L1 and it will be equal to 2 pi R1 because the radius of this loop is R1. Okay, so what we get is the magnetic field we considered as B1, the Amperian loop we have formed is of radius R1, and for this loop the magnetic field is B1. Now length of this loop 1 is L1, that is equal to 2 pi R1. Now if we see the diagram, the current enclosed by this loop is actually 0. There is no current that is enclosed by this loop. So while applying Ampere's circuital law, what we have is the line integral of magnetic field over the closed loop is equal to the mu naught times of the total current inside that loop, and the current is 0 here. So in loop 1 there is no current, that means I is equal to 0. So when we apply Ampere's circuital law for loop 1, we get B1 L1 is equal to mu naught I, but I is actually 0 here. So B1 L1 is equal to 0, or what we get is the magnetic field B1 is equal to 0. This means that since there is no current inside the Amperian loop 1, so the magnetic field at any point P in the open space interior to the toroid is 0, or in section number 1 the magnetic field will remain 0 for any point in section 1. For any point P in this region, the magnetic field will always be 0. Okay, so this was about the region 1. Now we are moving to the second region, that is for the points inside the toroid, just like S. So we are talking about the points inside the region S. We are considering that the magnetic field, this green line actually shows the magnetic field and its direction. So we find this direction by using right hand thumb rule that we have studied earlier, but now we are talking about the magnitude. So let us consider the magnitude of this magnetic field be B2. Okay, and the Amperian loop that we have here is the second Amperian loop or loop 2 of radius R2. The length of this Amperian loop is L2, that will be given by its circumference. Since its radius is R2, so the length will be 2 pi R2. Okay, now let's talk about the current. If capital N is the total number of turns in the toroid and I is the current in that toroid, करंट I फ्लो हो रहा है हर लूप में से and there are n turns in the toroid, then the total current enclosed by the loop 2 is actually n into I, capital N into capital I. So let's see what we have for any point inside the toroid. Let it be S. The magnetic field has magnitude B2, this we assume. Now the Amperian loop is present there of radius R2, we call it as loop 2, and the length of this Amperian loop or the loop 2 is 2 pi R2, that is the circumference of that loop. If capital N is the total number of turns in the toroid and I is the current in the toroid, then the total current present in the toroid or the total current enclosed by the loop 2 is actually capital N into capital I. Now we are ready to apply Ampere's circuital law, and according to Ampere's circuital law, B into L is equal to mu naught I. That means here B is B2, length is L2. mu naught into total current. So B2 into L2 is equal to mu naught Ni, and by substituting the value of length, that is 2 pi R2, we can find the magnetic field B2. Now let's see in the diagram, we have considered a random point S. Now this point can be here, can be here, can be anywhere inside the region. So this R2 will vary with point, the circle will vary, and accordingly R2 will vary. So we consider that this R2 be the average radius. Okay, what we considered, that this R2 be the average radius, and small n is the number of turns per unit length. So if small n is the number of turns per unit length, and if I multiply it by the average length, that is 2 pi R2, because I considered R2 as average radius, so the length 2 pi R2 is the average length, and if I multiply that average length by number of turns per unit length, I will get the total number of turns, capital N. So we assume that R2 be the average radius and N is the number of turns per unit length, then total number of turns, capital N, can be given as number of turns per unit length into length, that is N into 2 pi R2. Now I am going to substitute this value of total number of turns in the equation of B2, and we get as 2 pi R2 and 2 pi R2 will cancel out, and we get B2 is equal to mu naught Ni. So this is the magnetic field present inside the toroid. So this is the magnetic field for any point present inside the toroid. This was about the section number 2, that is inside the toroid. Now moving to the third section, that is for the points in the open space or exterior to the toroid. Let's see in the diagram. So if we want to find the magnetic field at the points that are exterior to the toroid or in this region, so we create an Amperian loop here of radius R3, but for applying Ampere circuital law, we plot Amperian loop, we should have some current enclosed inside the Amperian loop, right? So in this case, in the case of exterior points, the current that much coming out of the plane will enter inside the plane. Means this whole Amperian loop enclosed turns, in those turns the current coming out of the plane of paper is actually cancelled by the current going in the plane of paper. That means jitna current in point se out of the paper aayega, that much current will go inside the paper by these points. So ultimately these currents will cancel out each other, and the current enclosed within this Amperian loop 3 will be 0. Okay, so each turn of toroid, because of the each turn present in the toroid, the current coming out of the plane of paper is cancelled by the current going to the plane of paper. So because of that, the net current enclosed in the Amperian loop will be 0. Since the current is 0, so mu naught into total current, that right side of the Ampere circuital law, will be 0, and the net magnetic field at the exterior points will also be 0. So for points in open space or exterior to the toroid like Q, we have for each turn in the Amperian loop 3, the current coming out of the plane of paper is cancelled by the current going into the plane of paper. So if we apply Ampere circuital law, we get the equation B3 L3 is equal to mu naught I, where this current is equal to 0. Because of this 0 current, the net magnetic field for the region 3, we get the total magnetic field at the point in the open space exterior to the toroid will be 0. So this is the magnetic field for third region. So basically what we have in region 1 and region 3, the magnetic field will be 0. It is only present inside the toroid, or the points that are present inside the toroid, and is equal to mu naught Ni, where N is the total number of turns per unit length. Unit length में कितने total turns हैं, that is N. We can also show it as, तो sum up कर दिया हमने सारे अपने calculation और results को, that the whole toroid is divided into 3 sections. We get 3 kind of points here. First, that is those points in the open space interior to the toroid. For those points, the magnitude of magnetic field will be 0. This is 0 because there is no current enclosed inside that region, inside that loop 1. Okay, now for the second region, the magnetic field is mu naught Ni, where N is the number of turns per unit length that we have calculated. For the third region or the exterior points, current is enclosed by the loop, but jitna current coming out from the plane है उतना ही going inside the plane of paper है. That's why the net current that is enclosed by the Amperian loop is 0. मीन्स लूप के अंदर करंट है बट जितना करंट प्लेन के पेपर से बाहर आ रहा है उतना ही उसमें एंटर हो रहा है. दैट्स वाई इट कैंसल आउट ईच अदर, and because of that the net current enclosed by the loop Amperian loop 3 is 0. Since that net current is 0, so the magnetic field is again 0 in this case for the exterior points. So this was all about the magnetic field due to a toroidal solenoid. In the coming videos we will be studying about the magnetic forces acting on the moving charges in a magnetic field. So till then you stay tuned and keep studying. Thank you.